starting. So my name is Joel. I'm a research scientist at Spotify in London. Today, however, I'm not presenting work from Spotify. I'm presenting some work I did with Booking.com during my PhD, which I finished about half a year ago. So it joined work together with Yuri and Dennis, who are researchers at Booking, and my two PhD supervisors, Stefan Feurigel and Gloria. And small disclaimer, this work is mostly on econometric methods and some light theory, but it has some motivation and application to platforms. So I thought it could be interesting to this audience. So we know now that recent research over the last couple of years has shown that prediction models based on machine learning may be biased in a way that systematically disadvantages people from certain groups. So, we have a couple of examples here that I'm sure you have heard or read about. And what we consider this paper then is that this kind of algorithmic bias across groups may also arise in models of heterogeneous treatment effects, which we heard about yesterday in the paper about Twitter. So what we also know is that platforms, in particular tech companies, and many other companies, also those in healthcare, now routinely use these kind of models of personalized treatment effects to evaluate and inform interventions, for instance, about whom to target. And therefore, it's important to detect and be able to mitigate group-wise biases in these models to not have downstream, group bias in inference and decision-making. So what we consider in this paper is a general, quite simple framework for detecting and mitigating algorithmic bias in predicted heterogeneous treatment effects. And we will show that the problem of detecting this can be framed as a general estimation and inference problem. And then how to actually address it can be quite tricky. It will show some kind of fundamental challenge there. And the problem or the general idea is that once you try to address it for new individuals, you might not be able to perfectly address the bias. So you must mitigate the risk of that any bias remains. So I will talk a little bit about that. And then the methods that I will show are intentionally meant to be quite simple, so they're scalable for use. We take the platform perspective. And they show the principle be applicable to any kind of prediction model without exactly knowing what it is. So we will not take like a structural approach and try to address it with more of a reduced form approach. And then we want to still the methods to have kind of some theoretical guarantees to work well in practice under minimal assumptions. And I will use some data from large-scale randomized controlled trials at Booking.com across the world. So just a little bit about the background empirical context that motivated work. So we use data from Booking.com, and in 2019, the following experiment was run. So Booking.com, they have users arriving to, for instance, the desktop version of the website, and they randomized users into one of two conditions. Either a treatment condition, where users randomly allocated to receive an offer of a free taxi. So I will just show you how that works. So, when you go to Booking.com or say Expedia, you make a search, which is a combination of a destination and a date range. You get a ranked result, and then you can click on your hotel choice. And for some of the hotels that were included in the campaign, you have these kind of offers here. Such an offer is breakfast included price. The people in treatment condition, they also got an offer of a free taxi from the airport as an incentive to complete the booking, right? The people who were not allocated to treatment condition, they did not get such an offer. And randomization into either group completed continued until both had 18.5 million. So it was 37 million observations. And I can just say also that, of course, in the control group, they filter out the people that did not search for the same hotels where the offer was. So there's perfectly comparable. And based on the data on that, they then trained some causal inference machine learning model to predict the intention to treat, heterogeneous treatment effect from these randomized data as a function of the user features. Some features we have about the user, about who they are, what kind of, if they belong, what country of origin they belong to, and how long they've been on the platform, behavioral characteristics. And then in 2020, they repeated the same experiment, but for new users, of course, but also then used the model to predict heterogeneous treatment effect. And they do that because then you can check kind of out of sample in deployment predictive accuracy of this model. Right. And now, and the motivation of this paper is that they're interested in learning if this model is systematically biased in how well it makes predictions with respect to where people come from, basically, the country of origin. Or I can say that this country of origin is not a protected attribute per se, per Dutch law, so Booking.com is based in the Netherlands, but it can be seen as a proxy of nationality, which is right. So this is what they wish to mean. Still, we know that, or Booking.com knows that country of origin is a strong driver of the heterogeneity of such a treatment effect. You can for instance think of if somebody from a country that is on average less, say, economically developed, just an example, they're probably gonna be more responsive to such a kind of price offering, which you might look at than from somebody from a highly developed country, say Switzerland. So as a response, we don't necessarily want to equalize the predictions themselves across countries, right? But we want to account for the heterogeneity if there is such. Right. So therefore we accept that predictions are different, but not that they're inaccuracies.
Can I ask a question?
Yeah, sure.
So what is the difference between the, so first, what is the difference between what Booking did in 2019 and 20?
Oh, it's
in terms of
exactly the same.
predictions.
Just that now they have the model, so they can predict it for everyone. Exactly the
So
same.
the reason for the 2020 experiment was simply do out of sample prediction.
Yeah. And basically check, they could also then use the model. Or, I mean, you can also see this now they've deployed it. That could be the example, right? But now they also, sure.
Why do you need an RCT?
Because then you can actually do the, if the model is inaccurate, I mean, you can do, if the model did not capture the true treatment effect, then you can still use consistent estimators thereof, right? That's basically the idea. Yeah. Okay.
And
yes.
One more question.
Yeah, sure.
If wouldn't we be able to detect larger heterogeneous treatment effects with greater accuracy?
In what?
Suppose some heterogeneous treatment effects were very close to zero.
Yeah.
Wouldn't they be very hard to detect with a fixed sample size compared to larger heterogeneous treatment effects?
Yeah.
I'm asking about the last bullet point. Given that HTTs vary across groups, is it possible to detect them with equal accuracy?
That's part of the point of this talk.
Okay, great.
Yeah, that's one thing that we think that bias is actually a thing that needs to be estimated. But that's part of the problem. Yeah. All right, I will just now highlight some general reasons why we could have bias in this case, right? So in the previous example, right, the training sample size, so per group, per country of origin, there might be completely different, right? Not necessarily the case that Booking.com has an equal number of users from US than say some other countries, right? So therefore the model might not be able, if it's trained on the global data, which it typically is in these platforms, because there's a conception that, more data the better, then it might not be able to fit equally well, right? Also, randomization was not conditioned on the group, right? So you might have an equal balance of treatment and control groups conditional on country. And it could also just be the fact that the joint distribution between feature, treatment, and outcomes vary by group, so the model is not able to capture it. So this is just a general reason why it could be biased from the data. You can also have it from the training of the model, right? Let's say that you have the model optimizes for mean squared error in total, right, and not per group. Then it also does not account for this. It could be that there's some unmeasured confounders. And it could be that these models typically use regularization. So even if it would include like an indicator of the group, if that is not necessarily found to be predictive, it's dropped, right? And it could lead that you have this kind of unequal regularization bias. So these are just general reasons. The main point is that in this talk, we will not aim to kind of characterize where the bias is coming from, but we'll simply try to find it and then mitigate it, what kind of the joint impact. So, yeah, sure.
It seems like you talk about both bias and the sort of variation, the sort of treatment effect at the same time.
Yeah.
Should I think about the bias or is it both?
Yeah, so the bias, good point, maybe can be clarified. So bias, we have both within group bias, right, which is typically a statistical estimation bias, right? The difference between the predicted heterogeneous treatment effect and the true one. What I will come to later is that given this, a reasonable definition of algorithmic bias is that this varies across groups, right?
So
That
this
is
is just bias.
Sorry?
It's not about the, I could have an unbiased predictor across groups, but just as Ken said, it's just super variance for one group, but because I have little data on them.
Yeah, so it could be, yeah, exactly. I mean, you could, if this statistical bias varies across groups, then we have a problem. Right, because then it's
You're
equally
giving a
accurate.
deviation from the realized lift versus the predicted lift.
Yeah, if
You're
that
about-
deviation varies by group, then we have a problem. That's what we consider in this talk. Okay, just a toy example, and this will illustrate it. So just to get the point across. So let's consider then that you have two heterogeneous groups, group A and group B. They differ both on average and within groups, right? So you can see that each, here you have the booking probability on the y-axis. Let's say that you use a model, right, to predict from the baseline probability per book, the increment you would get if they would get a treatment, right? So just the lift. So this is what the model gives. Now let's assume that in truth, right, the true heterogeneous treatment effects are different in size for the groups and what you predicted, right? So you're not able to capture the truth. Then what happens, of course, is that the group error in the treatment effects is completely different across groups, right? It varies. So this is the kind of what we consider bias here, right? We're not able to equally characterize this or find these heterogeneous treatment effects across groups. So a naive approach to do this, or the simple approach, would be to use historical data to obtain these kind of group level prediction errors. And then once you have new arrivals come, you simply divide it by for each prediction you make, you subtract this, right? Yeah.
Well, sort of implicit argument is that bias is bad. You know, because when we think about shrinkage estimators, for example, we're intentionally inducing bias,
Yes.
right, for efficiency. So
You mean the variance would be a concern too? Yeah. Yeah, that's, I mean, when we come to mitigation, that's exactly what we'll do. When we come to actually how to address it, then we need to account for the variance because the bias is an estimate. That's the point. But just in terms of like a decent definition of algorithmic bias is variation in statistical bias. That's basically.
yeah, because I mean, a good shrinkage estimator should induce pretty strong bias in groups of them.
Good point. You could also view it as, I mean, I think the basic point of the talk is also you can consider bias as disparities in loss function performance. You could also do that. Yeah. Okay, so the problem here is, of course, that the treatment effects are unobserved, right? So the group error must be estimated. That's basically the point. And if we would do bias by simply subtracting the point estimate, we neglect the uncertainty, right? The variance. That's the basic point. So simple approach of this talk is just to show then that this estimation inference detection is basically an inference problem per group. And then once we do bias, we must account for this. You can call it risk minimizing or uncertainty aware or variance aware debiasing. But that's basically that point. Okay, so just briefly on some related work. So detecting algorithmic bias requires some notion, right, of what bias means. So here, as we talked about, we just define the disparities in mean prediction errors at the group level or statistical bias. And it follows basically the tradition in the algorithmic fairness literature, mostly from computer science. And there they focus on groups, typically motivated by legal frameworks and so on. And here they focus on the focus of errors and not on the predictions themselves. That stem from that the treatment effect might vary across groups without there being necessarily a cause for discrimination. Right. And it might be a good point here also that most of the work is on binary classification. You want to classify somebody to, whether they should receive something or not, whereas here it's about the actual estimation task. And then you can also look about, now that you want to address it, we must have some method for mitigation. And you can basically, it's basically three ways to do it. Either you can use a pre-processing approach, which means that you apply you alter the training data such that if you would retrain your model, it would achieve your notion of fairness. Right. The second way to do it, second class of method, is called in-processing. And it basically addresses the mitigation during the training of the model. So given that you found that your model is biased, you retrain it, and you add some constraint, minimize mean squared error subject to that this notion of fairness is achieved, right? And talking to the people at Booking and thinking about it, both of these approaches can be quite, they seem like very reasonable, of course, but it can be quite difficult to achieve in practice. Because if you're a platform, it means that every time your model is found to be biased, you must retrain it. And that is very costly. Just not in time, just running a new maybe RCT to get new data. And then you have to pay all the machine learning engineers the salaries to re-engineer the model and so on. And also for external use, say if you're like some auditor, it might even be infeasible to approach it because you might not have access to the training data. And you might not have the actual compute able to run these optimization models, right? So instead, what we take is a quite simpler approach, which is called post-processing, which basically just means that you leave the model as is. So the model, you don't change the model, but you simply adjust its predictions, right? And then, just finally, how do we do this? We make use of some recent work or some different work in statistics and ML. So there's a long literature in statistics on the use of weighting and auxiliary information for debiasing and calibration purposes. There's also recent work in machine learning on how you can use RCTs to debias and machine learning predictions. There's a recent stream of papers in marketing that considers the calibration inference on these machine learning predictions. However, they use this kind of in-processing or a more model-based approach. And our approach is intentionally quite simple and is purposely so because it aims to highlight just some basic results and challenges. Right, let's get to it then. So what we consider here is, this is basically the data, right? So you have random variables on some pre-treatment covariance X, could be high dimensional, it's at the user level. You have some randomized assignment, capital T, it's binary, get a treatment or not. And then you have an outcome that could be binary, say conversion, or continuous, say given a conversion. We have individuals from I to N, where the sample size might vary by group. Just for simplicity, we will not index any random variables. It's not needed. We have a set of groups, which is known and finite, can be big. Like in the Booking examples, it's about 200. It's all the countries they're active in. And then these random variables are sampled from a unknown joint distribution, conditional on each group, right? So the joint distribution of the data might vary completely arbitrarily across groups because people are different from different groups. So what is then a heterogeneous treatment effect, right? You can think of two different ways of defining one. You can have what is a difference, which gives a magnitude effect or a linear effect. It's the standard one we see typically in economics and econometrics. And we can have what is sometimes known as a lift, right? Which is a relative measure, commonly used in practice because it gives percentage difference. So in this talk, we will focus on this because I think it's more interesting. It's also a more common one in practice at companies because, again, it gives percentage estimates and also it gets the points of the paper better across. And just here to be transparent, what is measured is, of course, heterogeneity around an average treatment effect in terms of observable features X. Yeah, the problem is, of course, these are not known. So we use a prediction model thereof, right? And the prediction model, we will not think about how it's estimated. It's just in some way estimated from the data in a way we can assume is optimal for the task. And it gives some predictions, hat fx, which we will also denote as tau hat fx. We consider the model to be fixed, right? So it's not something we re-estimate, but it's a black box, right? And importantly, this one did not need to, we do not assume that this one is like causally identified. That might be a reason for its bias, right? So the model could be arbitrarily bad as well. Okay, so what is then the problem? Well, the problem is that the predicted heterogeneous treatment effect are at the personalized level, but we want to assess bias at the group level, right? So we need some way of aggregating our individual treatment effects, so at the group level. So then we borrow a concept from the statistical literature. It basically says that such an individual heterogeneous treatment effect measure is collapsible to an average treatment effect if there exists weights of the joint distribution such that the weighted average of the heterogeneous effect equals the average effect. Right. So it's quite easy to see that if you would use this above measure, then weights are actually not needed, and that's why we don't focus on that case. The most interesting case is the one in practice where you focus on the relative measure, because then you need to have these weights that account for that, the heterogeneity in the baseline outcomes with respect to observable features compared to the marginal average baseline. Right? Because if you don't account for this, then the weighted just the simple average will not equal the average treatment effect. And at a high level, what this means is that an average treatment effect can be recovered as a weighted average of the heterogeneous. And it might also be worth noting that some common effect measures, such as odds ratios from logistic regression, for instance, logistic regression, are inherently non-collapsible. It's possible to obtain like an average odds ratio as a weighted average of the conditional ones. So why am I telling you this? So you will see now soon why that's important. So the true prediction error for a given group we define here as the expected deviation of the predicted heterogeneous treatment effect from the true weighted according to the baseline, right? So it's analogous to the statistical bias of an estimator, right? If you view this quantity as an estimator, this is basically a weighted version of statistical bias. Right. However, it's not clear how we can do this because it depends on the true ones, but our model thereof is biased, right? So it's not necessarily feasible to try to estimate this because clearly we already tried to do so. So what collapsibility then gives us is that we can basically decompose this, right, into just the predicted A to E for the group by the model. So you take a heterogeneous treatment effect, you collapse them by weighting to an A to E, and then the statistical bias is just the difference to the true A to E. Right. So it shows that basically you don't need to actually know the true heterogeneous treatment effect to check how bad or its bias is, the statistical bias is for a group. So it basically reduces the identification estimation problem to a high dimensional one to a scalar one. I hope that's clear. And then given this definition, we say that we have algorithmic bias if this difference for one group compared to the pooled rest is different, right? It's very simple definition. And it says that the implication is that the model should be able to capture group heterogeneity equal well if such heterogeneity exists, right? So we don't make any assumption if the heterogeneity actually exists. And it's defined with respect to the true prediction errors that are observable, as that is what we want to detect, right? Yeah, and you see I also talked about it. It's not necessarily a problem if the predictions are cell-variant groups, because that's the motivation for the whole purpose. It is a problem if the accuracy varies. So let's now consider just the basic result. And I will omit like how we actually estimate it because that's kind of technical and not maybe so interesting. So I'll just jump to basically the results. Yeah, sure. Sorry.
I'm interested in that.
Estimation.
Yeah.
Okay. Yeah, I will talk. It's in the paper. I can talk a little bit about it. Sure. Yeah.
Just going back a little bit, so usually I'm thinking of bias like do I predict it on average correctly? This is not what you're saying, right? You're saying it's just predicting different variants of the HGs for different groups. Roughly, this is the
I say that for each group, for one group compared to the rest, we want the model to recover basically the heterogeneous treatment effect should recover on average the true heterogeneous treatment effect equally well. So they should be calibrated to an average treatment effect per group equally well.
So often I've seen heterogeneous treatment effects estimated, and they say they're honest or unbiased per group, right? So why would you get the bias if you use an unbiased method? Because
let's say that your, unbiased is on
On average.
On average, right? So let's say you have a big group, but you have for one group, 90% of the observation comes from one group and 10% coming from another group, right? Then you have a problem. Because it might not be able to be equally calibrated to the 10% as the 90%. It's going to overfit the 90% because they contribute more. They contribute more to the loss performance, like mean squared error.
That would not be fixed by the experiment because just a representation within the.
Yeah, I mean, you can fix it. You can fix it by the experiment. In practice, however, it's not really often done because in these platforms they often think that the more data you have, the better, right? So they will not fit the model to the 10% because why would you do that? You just fit it to the 100%.
I'm just trying to understand, is this like automatically happens all the time, or this is like, oh, if you think
It can automatically happen if your sample size varies. That's the point. Yeah.
But if your experiment cell sizes are different, because the type of, if let's say one cell is 90%,
Right.
the same type of error in the 90% is penalized 9 times more than the same type of error here. So my model tries to learn the 90% much better. So that's why you use counterfactual loss.
Yeah.
You reweight the cells, the observations, you reweight them down.
Right.
So that you predict along.
Right. That's a possible approach. You could do it. Yeah.
Yeah.
Also, that would be an in-processing approach.
Yeah.
Right, so this was my question.
Yeah.
It's possible to correct it, but you're saying it's just not done and then.
Yeah, exactly. And even if you would use an in-processing approach, it's still not guaranteed that it doesn't, like, it can still, right? That's kind of the problem. Yeah. Okay, I will go a little bit into estimation. So yeah, just assume that we have a consistent estimate of the true average treatment effect. So that is basically estimation task. So it could just be that you use a sample difference to mean, so sample ratio of means from a randomized controlled trials, right? Or you use a regression adjustment estimator, or your favorite machine learning, or even a structural model to get this. Right. Let's assume also you have some weights, so you can collapse your heterogeneous treatment effects to predicted ATE. Then we show in the paper that under standard assumptions that the variance is finite and so on, that their difference in the limit just converge, right, to this estimate at beta, which is a normal variable centered at the true bias, the unobserved one, with some variance that depends, of course, on your sample size per group. And the proof is actually very simple. You can probably if you've done some of this similar work, you can probably immediately see how it would be done. And that means that, well, I will also say here that in practice, you might want to split your data or use different data sets to estimate such an ATE and use the weighting. Because if you use the same data, you will have covariance between the two estimates, right? Because you use the same data twice. So you can just use data splitting. And then you can cancel the covariance, this was simplification. So what this gives us? Well, the asymptotic normality enables us to use standard t-test, even though the machine learning model is completely black box, right? So we can just use these test is null hypothesis. For instance, we can test for that the model is not, within group biased on average, the first hypothesis, or between group bias, algorithmic bias, also called between groups, right? And how would you do that? How would you get standard errors? I think to get the standard errors like in analytical form is quite complicated. Also because the model might be black box. So we say you can just use bootstrap. There's a similar approach in these two papers by Gordon in marketing science. You can rely on that. So you can repeatedly sample from your group and then just use that to get standard errors, right? And of course, these bias estimates or these biases are unknown. So what we do in practice we will check instead if our estimates, the analogs here, where these thresholds account for that, the true biases can be, or the difference between them can be zero, even though like in practice it's not, because we have some variance we estimate, right? So these thresholds, we show also in the paper how they are implicitly determined by the confidence level of your test and the sample size. So given this, let's not go to how we actually address it. And our focus will be on minimizing the risk that any bias remains when we predict for new individuals. So the first problem then is, if our platform, how do we actually want to address this, right? So the objective again is to remove the group level bias for new arriving users that may have some new features, right? A naive strategy, but which is the immediate one you would think of, is to simply, once an arriving user with some X comes, you take their, you have your prediction, you have them in fit the model, you simply subtract the group error. Because then clearly on average, in the limit, right, it would be no bias left, right? You would think so. The problem is that this relies on frequentist statistical inference, right? Where we think of this as repeated hypothetical sampling, right? So such a strategy would aim to remove bias on average if we would have hypothetical repeated sampling. However, in practice, what we do have is of a given sample of new users, right? We have one fixed sample. And since the variance is not negative, right? If we just use such an approach, which might actually increase the bias, right? Because our estimate, which we debias with, might not equal the truth, right? So the basic approach is just that we should account for the variance, basically, when we debias. That's basically the idea. So what we frame this as is a optimization problem. So you can think of it then as another more general strategy is to debias according to some correction factor here, gamma in pink, right? And this gamma is set such that from 0, meaning that it would be 0 when we do no debiasing, or up to at most 1. So it kind of coincides, with this naive, what they call the naive strategy, right? So then what happens if we do this? If we then use such an approach, and then we have a new sample, and we sort of collapse our new weighted, so we take the weighted average of these new predictions that are the bias, then we arrive at this, right? So we have the collapsed new heterogeneous treatment of the predictions that we have that correspond to predicted ATE. We have the debiasing term, and then we check again, corresponding to the true ATE, right? And that could then recover, the difference between this and this is the true bias, and then we're left with the remaining group error, right? So this is the bias that would be left in a given sample in practice after we debias according to our estimate up to some factor gamma. And then what our objective is of course to find such a gamma that would minimize the expected loss, what in statistics, right, is known as the risk of that there's any bias that remains, right? So we should find the gamma between 0 and 1 that minimizes the expected loss, over different samples we could have had to detect the bias, right? So it just follows this standard kind of empirical risk minimization principle in machine learning. And it accounts for the sampling uncertainty we have during the detection. That's what we account for now. So now we just show. So we consider 2 standard loss functions. You could consider more, but these I think is more common ones. So the first one is that you care about absolute error loss, right? So then what you arrive at is that the risk function will be the mean absolute error, right? And why would you choose that? You would choose this loss function if you care to be robust against realizations of your detection data that would result in outlier bias estimates, right? You could take the average, right? So then, very simple to see. What is the optimal correction factor? What is the optimal way to debias if you care about such risk? It's to if there is true bias, so your non-opposed isn't true false, then you simply debias with the point estimate. Otherwise, you do not, right? However, we don't know if the non-opposed actually is false. The best we can do is test it, right? So a feasible estimator is just to debias if this, our test statistic exceeds the critical value, right? And this depends, of course, then whether you should debias or not depends then crucially on 2 factors. It depends first on how well you're able to estimate the variance, right? So if you're unable to estimate, well, it's noisy, then, right, you're less likely to debias because your data is kind of uninformative of what the true bias is, right? Yeah.
This beta hat G is the empirical bias.
That's the empirical, yeah.
Aren't you better off do some learning across groups for this beta?
You're sorry,
Aren't you better off do some learning across groups for this beta hat G?
you could do it. I mean, you could get it. You could, of course, also estimate this, saying use like a random effects model where you pool across groups, but then, deviations. Of course, you could do that.
But this thing is anyways going to be biased a little bit because of that gamma. Gamma is never going to be one, right?
No, but gamma is something we set now. Gamma is something we set according to the estimation of this. So gamma is something, it's not something that's necessarily estimated. That's of course we have a hat here, but it's something that depends on the estimate of the bias and the variance in the bias.
So let me see whether I understand this correctly. My intuition was this gamma, you're trying to do some bias variance trade-off. In one, it's just quote unquote unbiased, but you have sampling error. You want to tackle that. So you want to partially get it out. That's why you're trying to optimize this gamma.
Yeah. We want to set gamma such that we also account for the variance.
The variance in beta hat G because it's
The
negative.
variance in beta hat within a given sample, yeah.
Okay, so my next question is, given that this thing is anyways not gonna fix the bias fully, aren't you better off learning that beta hat G across groups?
That's another approach you could do. That's not something to consider. It's an interesting alternative, yeah. I would have to think about it a little bit. The point is that if you would do this perfectly, though, then you would per group, if you could do it perfectly, you would per group, of course, omit the within group error such that then there is no between group difference, right? That's the basic argument. So our point is basically simpler, I think, than what you're trying to make, but it seems like a good.
My worry is that beta hat G is super inefficient.
It could be. I mean, you could also, of course, use. It depends on your estimated usage. If you use just sample average, I mean, in our case, we have a sample set that's quite big. It's in the millions, right? So it's quite efficient still. If our sample was be small, we would not use such a naive estimator. We would use something, much more complex, like a high-dimensional regression model or something, right? Good point. Anyway, yeah, it shows you that first the variance sort of affects whether you bias or not, but also the confidence level, right? So, and just also here to avoid kind of the whole post-selection inference problem, of course, you want to set the alpha before you do this test, right? And you can set it, for instance, to the standard level or a type 1 versus 2 type level. And then we can also care about, of course, squared error loss. And that gives us then the remaining bias and the mean squared error risk function over the bias that remains in squared sense. And this we would care about when we want to penalize the data realizations used for detection that produces outlier or high variance estimates, right? And then we show it's just some derivations. What you do is that basically you set up the squared error loss, and then you solve for the first order conditions with respect to gamma. And then you arrive at that the risk minimizing in the mean squared error sense correction is to set gamma such that this way, if you would know them in truth, right? However, in practice you don't know them, so we can rearrange terms and then just basically use algebra, and you arrive at these two approximations. And what they just show you, just say the first one here, for instance. The first one says that if you care about minimizing mean squared error of remaining bias after debiasing, then you should set the correction factor to your estimate of the bias per group over, say, the average of bootstrap estimates thereof, right? Or you could do it to the right, where again you use bootstrap estimates, but also the variance bootstrap estimates, yeah, to correct that. And what this shows is that it adjusts the biasing per group with respect to both the square, so the magnitude of the square, is a measure of magnitude, and the variance. And it also shows that, if you consider one class of equally good estimator in the sense that they all produce this equally well, then an estimator that has lower variance means that, in the sense that your data is more informative, or the estimator is more informative, the true bias, then basically the mean squared error correction will collapse to the naive strategy, right, that I had at the beginning. Or if your data is uninformative, or your estimate is basically worthless, so that the bias is infinite, then you should not, of course, debias, because you have no information about the true bias, right? Okay, let's now, in the last 10 minutes, consider the application. So we have two RCTs, right? We have 2019 and 2020. The 2019 one was used for model selection and variable selection, right? To fit the model. So we cannot really use that data again, because then we end up with the problem that we do inference on the same data used for estimations. We just use the second data where we had the predictions. And yeah, I mean, this, in the interest of time, I won't spend much time here. We basically split the data in half. We use one half for detection, one half for the biasing, repeat it a lot of times, and we check how often it is. And this basically mimics the main characteristics of an online, if we would do this in practice. Okay, bias estimates. So now we're looking at the distribution of the within group error across groups and the across group distribution of the between group, because we care about the distribution of performance here. So what do we see? We see first that on average, within groups, the model is not perfectly calibrated, right, to the true AB. So this is centered, just for reference here, these are scaled to the standard all estimates here are scaled to the standard deviation. So they range from -+2 standard deviation, and this is the mean bias across groups. So yeah, we have an average error, both in terms of within group errors and between group errors. And we also see that it's a large disparity in the sense that the distributions are wide. You know, some groups are subject to 2 standard deviations worse within group errors, and errors that are 2 standard deviations worse than for prediction error for the other groups. If we then look at the inference results, what I've done here is that we've plotted the test statistic of the null hypothesis of no between group bias, and we compare that to the theoretical distribution of the distribution under the null. And we see here that at the 90% confidence level, there's all the groups that fall under here would then be a contamination subject to it. At the 95% level, out here, right? So then, quickly to the mitigation results. What we do is that we apply these different correction factors, and we see what bias then remains, right? So first, we see that the distribution is shifted more towards the center, both in terms of within group prediction errors and between group errors. So we can say that they sort of calibrate these collapsed heterogeneous treatment effects to recover the RCT estimates on average across groups. We also see that the width of the distributions are narrower, so we reduce the disparities across groups. And importantly, the naive strategy that neglects the sampling uncertainty has the worst performance since its density is lowest at 0. So that the fact of not accounting for detection is an estimation task sort of performs worse when we want to actually mitigate. So, yeah, summary, I will not go through this. I think you heard enough about that. I'll talk a little bit more about contributions. So at the broad level, we know from recent research that observational causal ML methods may not recover ATEs from RCTs, right? What this show, or it could be basically 2 problems, right? The first one could be that your identification assumptions do not hold the observation data, right? You can't undo the selection. The second one could be a modeling problem in the sense that you need to use a model that's robust against that. What we aim to show here is that heterogeneous treatment effect predictions may not be calibrated to the average effect equal well across groups, even if the model is not observational, but instead it's actually trained on RCT data and thereby actually satisfy all causal identification assumptions. Right. That is quite an important finding, I think. And this could be different kind of data problems. It could be representation bias, treatment randomization bias, etc. It could also be a modeling problem that we talked about, also a global fit across groups, unequal regularization bias, or it could be what we, a new kind of problem, but we just call it alignment problem, whatever. It means that the predictions that you collapse over in terms of the groups in error do not align with the distribution that the data was trained over, right? And this we think is kind of relevant irrespective of whether you care about fairness or not. The second one, more about the fairness, and I'm going to close after this, is that we think there's a personalization fairness kind of trade-off. So pursuing, what we show here is that pursuing, or first start from recent research, pursuing fairness at the individual or group level can induce us like inefficiencies within that level, right? So that there's a prediction accuracy trade-off given within individuals, or if you care about groups, within groups. But what we try to show here is that there's a trade-off also between the two levels of analysis, so individuals and groups. So, and the reason is that heterogeneous treatment of predictions aim at maximizing prediction performance at the personalized level. So we consider personalized heterogeneity. However, most common notions of fairness aims at removing heterogeneity in some way, either the prediction levels or the heterogeneity. So they're kind of at odds. And what this requires then, that if your models are perfect, you must shift. You must kind of actually, to get unbiased at the group level, you must kind of bias, right, your individual predictions. So, and then maybe an interesting question is, to what extent do we accept that maybe personalization gets worse in the pursuit of group level fairness, right? Kind of an interesting question to think of it for. Thank you. That's all I have.
Okay, so my name is Michelangelo Rossi. First of all, I would like to thank the organizer for inviting me here and for selecting this paper. Let me discuss it. So I am studying, working also on discrimination online. Not exactly, I don't work exactly on algorithmic type of discrimination, right? I'm kind of a reader, casual reader of this literature, but I would say that this paper is actually pretty good in giving you a broader framework. I will probably suggest, I already talked with Joel a bunch of times, that for a publication, right? Probably this part I fear that the editor will decide to cut it. But the paper, the working paper, this version is actually there. It's actually on the website, and I really will suggest to all of you, all the people who are interested in algorithmic bias, to also to read this quite nice discussion that Joel and his coders wrote at the beginning of the paper, right, to give a broader idea about the problem. Okay, so let me start talking about something that I guess all of us are aware, right? We know that machine learning algorithms can be biased, right? And they can sometimes discriminate minority groups. We have some accusations. We have also, some papers that are somehow showing that this could happen, right? But here, this type of analysis, right, is a kind of analysis in terms of outcome, right? And for this type of discrimination in terms of outcomes, we do have a framework. Interestingly enough, now today there is no MK. But this type of analysis is actually pretty similar to the type of controlling on observable framework that she talked about once she was talking about a totally different type of bias. Now it's interesting that this type of literature do not really talk about, right? Talk with each other, like the IO literature and the labor literature, at least in economics. And I'm very happy, to be in a conference in which we could talk about these issues in similar ways. Okay. But okay, so until what we talked here about, right? We are thinking about discrimination in terms of outcome. And as I said, we kind of have a framework. We can discuss it, right? We can go paper by paper, situation by situation, and see whether or not we are doing a good job. But more or less, we know what we are talking about. Yet, platforms, actually not only platforms, also firms, scholars, right? We use machine learning techniques to estimate heterogeneous treatment effects. And then the question is, okay, but is it possible, right, that we could also have algorithmic bias in estimating these treatment effects, right? And it's actually interesting, right? Because once we do this type of, task, we want to, treat differently different users, right? But that does not mean that we are discriminated against them, right? So I think we need a framework to understand, right? For understanding what we mean by algorithmic bias, but not in predicted outcomes, but more in terms of predicted pre-run effects. And I want to, I think that Joel and his co-authors are trying to define this framework, and I find it very, very interesting, a very interesting. So let me start again, right? I just want to come up here and, I'm not a econometrician, so I'm not going to in my discussion, I'm not going to focus on the technical part, but mainly on some few broad points, right? First one, right, is I would say about the contribution, right? We know, and Joel mentioned this a few slides ago, right, that we know that causal inference models for average treatment effects from observational data may not recover the average treatment effect estimates from randomized experiment. Okay, that's why we need probably an identification strategy. But it is true also when we train, once we use trained on experimental data. Okay, but then, and it is this point, well, also heterogeneous treatment effect estimates from machine learning model may also differ from the experimental HTS, right, for different groups. Now, after you realize this, you kind of understand that this is useful also for platforms, for us, for everyone, right? But this can also be used as a framework to measure and then probably mitigate, reduce, remove bias of machine learning algorithms to estimate HTS for different groups. Okay. Now, if you kind of agree with this type of I don't want to say we frame the paper, right? But if you kind of agree on this type of frame, then I believe that we can think about, about this paper in this way, right? So we define algorithmic bias as a statistical testing problem, right? It is essentially this inequality, okay? And Joel and his co-authors ask the question, okay, how can this bias be mitigated? And they provide a scalable post-processing approach to reduce this bias. And finally, they look at Bookie.com, right? And well, they try to observe, right, use a specific case and show that sometimes somehow we can eliminate or at least reduce the bias once we look at different groups. Okay. Now again, let's be back about what I said before, right? So what Joel is talking about is clearly relevant for fairness concerns, but it's also relevant for all of us, for platforms, right? So I believe that somehow this could create a tension between platform motives and fairness concerns. It is not exact. I mean, I totally understand that, here I'm not talking about the estimation procedure, and probably there are better people here in this room to talk about that. But then the question is that probably the paper could benefit from at least a discussion about this. For example, Bookie.com, I believe that it was interested in doing this because they care about not having a biased measure of this HTE, but probably it's not because they care about fairness per se, right? So the question is, okay, but which groups do we want to choose, right? And how many groups? So, for example, if a platform like Bookie.com wants to debias the heterogeneous treatment effect for some groups, does it lead to a reduction in the bias for other potential groups as well or not? I know that this is probably almost another paper or another type of questions, but I think that in terms of policy concerns, I think it could be very relevant. For example, right? Look at the Booking.com example. In the paper, right? I think Joel didn't have so much time, but they show, right, that the heterogeneous treatment effects algorithm bias is removed for different countries. They look at different countries. Okay. Now, what happens to groups that may correlate with countries? Say, for example, that users from, say, Spain versus France, right? The share of women and men, right, or different other groups may differ across countries. Once you remove the bias for countries, are you worsening the bias for gender? Or is it related? is it somehow related? I think this could be relevant, right? Because it would be interesting to understand whether once you try to reduce a bias over a dimension, what happens to other dimensions that could be relevant. I totally understand that it's very difficult to observe this and to have a theory, right? That for all cases, but of course, if you could have some evidence also looking at booking.com, I think it could be very interesting. What about other groups that are probably nested within countries? So if I care about Spain, okay, but what about if I care about, say, regions of Spain, right? Is somehow the bias reduced once I look at regions, right? Again, this I think is also relevant once we look at the previous tension that I mentioned between platform and fairness concerns. Oops. Yes. And then, okay, how many groups, right? So, of course, we would like probably to have all, the more groups, the better, right? Probably not. Of course, sample size is going to matter, but also, I guess the variations for nested groups could be relevant. And let me probably, I just want to stop almost here, around at 10. So let me just conclude with a minor comments. I know that we already discussed about that. So the definition of algorithmic bias for Joel is essentially this one, right? And I totally understand that this one is a necessary condition to have algorithmic bias. I'm not 100% sure whether this is sufficient, right? And I'm thinking, for example, what I propose, well, probably you kind of need absolute values also in terms of bias, right? Because if you don't have them, potentially, right, you could look at compensating biases that could lead to a situation that you don't address. I know that this is probably a minor point, but I think that could be useful to address this. So let me conclude saying that this paper again has been quite an interesting read, and it presents a statistical framework for detecting and mitigating algorithmic bias, and fairness considerations are relevant for this type of analysis, but this is also relevant for platforms. And I also believe that the type of post-processing approach is extremely useful, and because it's scalable and it can be used by platforms for self-regulation or not, and for regulatory audit. So I definitely believe this could be a very interesting tool. Okay. Thanks a lot.